Hi, I'm Joe McGrath. I'm a solutions design lead with Hy-Tek Intralogistics. And I wanted to take a little time today to talk through some interesting combinations and arrangements of pallet building systems. Not focusing just on the specific robots that are going to actually be manipulating and moving around items, but what are all the systems that feed that, and how do you make a full arrangement of a system that meets the needs of the operation? Okay, so let's talk about tote pallet building concept. So we're going to focus today on totes. It's a pretty simple, repeatable type of item. Sometimes when we get into cases, we were talking about lots of different variation, different package types, sizes, shapes, weights. So to keep it simple and to focus on the system level flows today, let's just stick with totes. The automatic building of pallet loads is a pretty important consideration for a lot of operations. It can improve many areas of your operation, and think about things like general capacity for the whole building. So maybe you only have 10 people that can work your dock, but you need more capacity, and you can build in additional capacity through robotic palletization. Or maybe even a more traditional unit load form or something like that to really amplify what that operation can do. Additionally, like it can improve the utilization of your labor. So instead of having somebody waiting at the end of a line for a box to come down so they can stack it, or a tote to accumulate on the line before they walk over and deal with it, you can have the robot do the waiting. And the robot's going to have utilization issues as well, but it's not going to be a labor utilization. You're not going to be paying for it by the hour per se. So it can really you can really make sure that your employees are doing the most that they can do, and it's going to be a little bit more satisfying and a little bit safer operation at the end of the day too. So a lot of these totes, and really when we're talking about palletizing things, these things can be heavy and they can be difficult to get onto the pallet. Sometimes you have to step onto a pallet and lean over, holding upwards of 50 pounds. Sometimes the things are heavier than 50 pounds that you're moving around, and that's actually very difficult to do. And there's a lot of reaching and twisting and bending that it ends up happening in the pallet build operations when they're manual. And a robotic version of this can really clear up a lot of that issue. And the other thing is, when you automate a process, oftentimes, if it's done correctly, you can reduce the number of human errors that tend to occur. A person's busy, or a person misses a digit or something like that, or forgets to scan, or they thought it scanned and the RF didn't beep. So you can reduce or eliminate sometimes these errors that happen in the pallet building process. Maybe you shipped a tote, but you didn't actually manifest that tote, and that could be a big problem. So this is a way to get around that as well. So here we're going to discuss a uniform pallet of totes. We're going to be building it. We're also going to be focusing on something that's really a single item, right? So these aren't like different size totes. And we're going to be focusing on solutions that are fully automated. There are a range of manual pallet building operations that I think a lot of folks are familiar with today. You pick up the tote and you stack it on a pallet. There's also some semi-automated solutions. We're not going to dig into them today, but they're also pretty interesting from a capital expenditure and return on investment perspective. But today we're going to focus on fully automatic systems. So the first kind of solution set we wanted to look at was a simple palletizer. So this could be something like a single 6-axis robotic arm that grabs a tote off of a feed line and then stacks it onto a target pallet. Now, the simple systems are going to have the more simple robots. They're going to have minimal reach. So you're only going to be talking about 1 or 2 target positions, really. When you start adding more target positions, the reach of the robot goes up, and it becomes a little bit more complicated, a little bit bigger, a little bit more consideration into the speeds of that operation. Additionally, we want to look at different methods with which that robot can grab things and put them onto the pallet. So I think we all understand that you can grab one tote and stack it onto a pallet. That's actually a pretty repeatable and pretty common process. But you can grab a row of totes and stack those onto a pallet. So in this case, based on the image I have on the screen here, we have one tote at a time on the bottom, and in the middle robot cells we have 3 totes at a time. So a row in this case would be 3 totes. There would be a left row and a right row. And additionally, you can have a robotic arm move a layer of product at a time. This is a pretty popular methodology depending on the type of product you're moving. And the reason this is popular is because the more things you pick up at a time, the faster that robot can hypothetically be. So let's say a cycle takes me 30 seconds. It might take 32 seconds to move 6 of something, where it takes me 30 seconds to move 1 of something. So, a little bit of incremental increase in the time to pick up that load, but a pretty substantial increase in the amount of totes per hour that a cell might be able to produce. So that's great. So we can increase the number of totes we move at a time. That can make our robot cells faster, and we could hypothetically have less of them. But at a certain point, you might need more robotic cells. And why is that the case? So let's say that I have a robot cell that can put to 1 or 2 pallets at a time. Or I have a robot cell that I want to go real fast, so I need to give it rows of product or layers of product. But when I do that, I also imply that I have the same destination totes all grouped together. So when I pick up a row, everything in that row needs to go to the same pallet. Some operations will have many, many destinations they need to sort to. So let's say I need to sort to 40 destinations, but I really only have 2 or 3 or 5 robots to do that with. Well, that might be absolutely the right amount of robots for the rate that you need, but 3 robots isn't going to service 40 different target pallets simultaneously. And additionally, if you have random arrival of totes to a robot cell, you can't guarantee that they're going to arrive in sets of 3 for one destination. So you have to do a little bit of magic before it gets to the robot cell. And here's where we get into robotic pallet building systems. So we can do some stuff called buffering and sequencing. So buffering is really just storing things in an interim kind of random access memory situation until they're needed or triggered by some other part of the process down the line. You're trying to soak up the slack or the variation between 2 different processes. And buffers are a great way to do that. And sequencing, so this idea of sequencing is changing the order of arrival of things. So maybe in this image we have, on the left side, we have totes arriving in 1, 2, 3, 4, 5 order. But on the right side of that robot, we want all 1s to arrive first, and then all 2s to arrive second, and then all 3s. So we're changing the sequence from a rainbow sequence to a very specific sequence that will allow that robot cell to do the most efficient work. Now, there's a few ways to do this buffering and sequencing at this kind of level. And some I think we should talk about, or they're interesting to talk about. There's conventional ASRS, so these are like mini loads, and we'll show what one of those looks like in a moment. We have robotic ASRS systems. So in this particular image, we're showing some ACR bots and some racking systems. ACR is automatic case retrieval. So these robots will go in and grab cases and move them around. You can achieve a similar effect with buffer conveyor. So you can have a sufficient length of conveyor and a sorter, and you can do something pretty similar. Now, if the tote count gets really high, that starts to become difficult, and we'll kind of step through that as well. So this is an example of a mini load buffer. Now, in this example, what happens is totes will come in kind of on the north side in a random order, and a crane will grab a tote or many totes at a time and put them into its racking system. Those racking systems for mini loads can be very tall. They can exhibit extremely high levels of product density, and oftentimes you use them to store product for like case level operations where you need a lot of storage, but maybe you're not 100% sure that you need huge amounts of rate. Right. And you can double up aisles and increase rate. You're going to also add some more storage when you do that. So there's a lot to consider here. But in this case, we're going to feed this resource, this buffering resource, and it's a mini load in this example, random totes. It's going to put them away. And then while it's putting them away, it's going to do an interleaved move. It's going to take its put away and combine it with a pick at the same time to save travel distance. So it's going to go in there and grab the totes that it's been requested for by the robot cell. So the robot cell is saying, hey, give me all the destination 1 totes. And it's going to put away some 3, 4s, and 5s. And it's going to go find several destination 1 totes and bring them down and put them on that south discharge line. And it's going to go to the robot, and the robot's going to build a nice little pallet, and we'll be happy. You can have multiple robots attached to that same discharge. So that's what the image on the left kind of displays. So here we have 3 robotic cells attached to the discharge of this mini load crane. Now we have a pretty great system, right? We have 3 robots. They'll always get exactly the right sequence of totes to build the pallets that they need to build. They could build any number of destinations provided they get the totes in the right sequence. And there's a ton of buffer. So they can work continuously ad infinitum, really, until that buffer's exhausted. So you have some great machine utilization. You're also removing operators from the equation, and it really is the dream. Now, one thing that would make this concept kind of challenging is that the crane is going to be a bottleneck for this operation. So maybe you'd like to explore, if it was a faster system, let's say, maybe you'd like to explore a type of buffering and sequencing solution that has some more higher rate characteristics than a single mini load crane aisle. But if it was really slow and you had lots and lots of destinations, this might be something to consider. Now, I'm going to go back one slide, and we'll talk about this ACR style buffer systems. This is pretty interesting. So here we can have a set of racking somehow in between the in-feed conveyor and the robotic cell. Maybe we have a bypass in there. It's not really drawn because we're trying to keep it simple. But the robots will grab it, and the robots, you can have many robots, and you can scale the throughput of that system by adding robots. Robots will grab it from the in-feed line and stuff it in these little rack locations. And then when it's requested by any of the robots on the other end, they'll go grab the right totes for the robot's request, and they'll take it to that cell and they'll feed it into the cell. So it does a really similar thing to the mini load example, but you can have a many-to-many relationship with the in-feed line or lines, the robots that work the buffer, so you can scale those up and down, and then the robots that are actually building the pallets. This is could be a very high rate system. Now, maybe not the highest rate because you have to touch everything, or you have to touch a lot of things twice. So that is a consideration for sure. But excellent flexibility, excellent scalability. So you can start small and then add these chunks of rack or additional robots over time incrementally. And it's definitely something to consider. Now, let's look at something that could be fast, but can't necessarily handle tons and tons of variation. So this is on the other end of the spectrum here. This is a conveyor system that will buffer. So it has a loop. It's like a recirculation loop. So things come in on the left side and they ride around this circle until they're needed by the robot. So a conveyor system can buffer things to the extent that it is long enough to hold all the totes or the items that it's buffering. So this is kind of the catch with this type of system. But as soon as something is needed and it passes by a divert or passes by the robot cell that it's needed for, it can go ahead and discharge, get to the robot cell, and you're good to go, start building that pallet. This might be effective for systems that don't need huge amounts of buffer, but do need to move pretty fast. You're really only touching it in and then touching it again out when the robot picks it up, versus the mini load example where you have to take it and put it into a rack and then take it out of the rack and bring it to a robot, et cetera, et cetera. So this could be a little bit better for those. But the issue would be when you have large amounts of buffer. So if you want to have lots and lots and lots of totes in queue, this might not be a great solution. You might want to look at a mini load or an ACR style buffer or something a little bit more robust in its storage capacity. Now, the solution, provided that we look at the data and all the math checks out, could be one of the lower cost solutions of the set that I just talked about here. Okay, so now we talked about really simple palletizers. There's one or two pallets that it's targeting. You don't have to have a big long arm. What if you wanted to target 4 or 6 or more pallets at a time? So you could conceivably have less reliance on this buffering or in-feed system, but you're going to have a more complicated robot cell at the same time. So here we're going to increase the number of pallet positions, and we're not going to have to buffer and sequence as much because we'll have more pallet positions, but as we'll talk, that's not always expressly true. The cells will be larger. The robot cells will be larger, and you'll have a greater degree of impact when you have to go into a cell and change out a pallet. So we did talk about that a lot on the first one, but when the robot finishes the pallet, that pallet has to be taken out, the full pallet taken out, and a new empty pallet put in so that robot can continue working. Now, but before, when I did that, I kind of only impact one other pallet. In this case, I'm going to impact the other 5 pallets in the 6 pallet system that are operating. And if I have multiple robot cells inside of a single safety zone, I could potentially impact all of them. So it's something to chew on. It's not always a bad thing, but it's definitely something to consider. And as the pallet count increases, and we've touched on this a little bit in the past, so too will the reach of the robot need to be longer. So now I don't have to just reach 2 positions. I have to reach 4 or 6, and I'll have to go further and further away from that in-feed point with the longest distance that I have to put tote. And this typically it results in a heavier robot because the arm has to be longer. Longer arms, more materials, bigger motors, et cetera, et cetera. So it kind of results in these larger systems. And kind of as in the previous methodology, we talked about inbound sequencing and trying to solve for those constraints. Here, we're going to focus mostly on the outbound sequence. So what I mean in this case is previously, we would use some kind of buffering and sequencing, feeding the robot cells to accommodate whatever changes in sort weight count or other issues we had. So we would buffer and sequence to the cells to solve whatever the problem was, kind of a high-level methodology note. In this example, what we're trying to do is have that buffer be more in the robot cells themselves. So we'll have more pallets available at any point in time. So I don't have to store up all my totes for pallet or for destination number 2. I can go ahead and send them to a robot cell that has destination number 2 available. So less buffering on the in-feed side, but more buffering within the cells themselves. So what does that look like? Let's say that you have to have 40 destinations serviced by your robotic system, but you don't want to have any pallet not represented at any time. So in a simple single system, we would hold all the totes for destinations that weren't being worked right now inside of a buffer. And here, we're just going to send them to a robot cell that has that. That means that we have to have all of those pallet positions available all the time. So this is a fairly simple in-feed system, but it's a little bit more complicated robotic cells, right? If we have 6 of them, they're bigger robots, and each of them has to be have sufficient rate to accommodate whatever load is generated by having whatever mix of 6 destinations assigned to it. So it becomes a pretty big system, or it can become a pretty big system, and it can take up a lot more space. It can be a lot higher cost. So here, in order to have 40 destinations, I have to have 1, 2, 3, 4, 5, 6 bots available to me. Whereas in the simpler system, I really only needed 3 simpler bots to handle 40 or any number of destinations. Now, there's a lot of trade-offs you make when you do that, but this is one thing to definitely consider. The other note on something like this, and we'll get into it a little bit later, is the high potential to overbuy capacity. So when you are designing a system, you want to look at how many things do I have to sort to? So how many destinations? And let's say it's 40. And then how fast do they need to build totes to those 40 destinations? Well, if we say it's 2,000 an hour and we build a system with 6 cells and it happens to be 3,000 an hour capacity, then I bought 1,000 totes an hour capacity of robotics too much, right? Alternatively, if I need some lower number or some different mix, the odds of me having a misalignment between how fast I need all the robot cells to go in aggregate and the number of destinations I need to service with all those robots, it's hard for me to make those two things line up every time in an arrangement like this. So we talked about this kind of briefly, but depending on how the pallet exchanging works, you may want to build in a bunch of extra space for machine access. So here in this image, we show a couple of different methods. So we have a robotic forklift coming in there. We have a person with a pallet jack going into a robot cell. And we have an AMR, a fork AMR, so a floor-to-floor style machine, going into a robot cell and changing out pallets. So it's definitely, safety is a big consideration with robotics. Ideally, robotics are left in their kind of own environment, unless they're a cobot type of thing. But in this case, you'd have to go through a safety barrier. If that robot cell is still working when you've passed that safety barrier, then it would have to probably operate at a reduced rate. So that everything else in that cell is going to suffer. Sometimes you'll actually stop the robot cell completely while doing a change out. And that's going to result in some lower robotic utilization than maybe planned for initially. And then while a robot cell is slowed or down for changing pallets, you're going to have to buffer any demand that comes to it at the same time. So those buffer lanes that are feeding the robot cells, depending on how you change out pallets, could end up being pretty long. So changing out pallet positions can be kind of painful, but are there some ways to change out pallet positions that can reduce the burden on that system? And I think that there are. So some things that we can explore, if that is the question, are pallet conveyor arrangements. So on the very top image, we have a pallet conveyor loop. So pallets ride around this conveyor, and the cases or the totes come to the robot on its same in-feed line we've been talking about the whole time. And we'll stop the pallet in front of the robot for the appropriate destination, and it'll grab the tote and stack it on there. Alternatively, we have the lower left image, we have pallet spurs. So we'll give the robot 3 pallets to work on in this example, and it'll build pallets, and maybe we'll only sequence those 3 to it. And when one of them is done, we're going to automatically take it away and then automatically drive a new pallet into that position with a conveyor. So it's just like, I say just like, it's like case conveyor, but very, very big. So pallet conveyor. And it's pretty tried and true technology, and it works. It's not terribly fast. So the robot now won't necessarily suffer the same safety ramifications as it would if a human entered the cell, but you do need to account for time to change over these pallets because it wouldn't be instantaneous. And then in the lower right, what we have is a pallet ASRS crane, or a stacker crane, they're often called. And here, we're just going to have the robot work in tandem with an ASRS. So ASRS will drop the pallet in its pick or put position. The robot will fill those up. And then when one of those is complete, the ASRS crane will grab that pallet, put it away in the racking system, or put it on a discharge conveyor, whatever the disposition needs to be, and then put a new empty pallet in that position. So this is a pretty interesting arrangement, and I've seen this a few times in my life, and it can be pretty quick. You get an excellent buffer kind of natively out of the system, so maybe going to the next downstream process or an outbound area. It can be pretty powerful. It's not necessarily very inexpensive. You have to build an entire crane. These are fairly large projects, so definitely something to consider. When looking specifically at the pallet conveyor delivery and takeaway, you do probably need to be a little bit more creative on this. So the changeover times, as we mentioned before, can be long. The loops, if you build a loop, you need to be pretty careful about what pallets are sequencing in that loop or what's working in that loop. So if you need like lots and lots of sortways, this could be a great solution. However, you want to be cognizant of the rate impact of constantly cycling through these. Now, there's also potentially applications where the pallets go so slow that you can place totes on them in motion. It's not something super great to plan on unless it's like a very specific application. And then kind of additionally, we want to talk about integrating a desired number of robots to a single pallet conveyor system, right? So we don't want to overbuy capacity. So can I put multiple robots on one set of pallet conveyor? Absolutely. Yeah, you totally can. And so we'll talk about what that looks like with another example in a moment here. But yeah, and kind of one additional note on these systems is because it's already on a pallet conveyor, you can attach the discharge of this process, so the finished tote, to all kinds of other systems pretty easily. So any ancillary process, like maybe you're going to put a lid or some slip sheets, or you're going to run it through a wrapper or a strapper, or you want to weigh and dim the pallet after it's done, or send it to some other system. Like, it's already on pallet conveyor, so it'd be a pretty easy presentation to do. Now here's an example of having some kind of technology to buffer your pallets, so your destination kind of target pallets, but then ganging up multiple robotic cells on that same system. So I don't have 3 ASRS cranes for 3 robotic cells. I have one crane that can service many robotic cells. So now I'm just sorting or sequencing the right totes to the right robotic cell based on the pallets they have in front of them or present. And these can be dynamic destinations too. So I can work a couple of fast movers and I can rotate my slow mover around. As long as the system's sorting the totes into the robotic cells and the ASR system are communicating and orchestrated appropriately, should be A-OK. So in this case, we're able to buy the right number of robots because we have this ASRS allowing us to buffer. So we don't have to overbuy in this case. I think this example is probably one of my favorites of the collection. This is technology that's fairly new, but it's also pretty popular in the market right now. So we have these floor or shelf-based AMRs. So these little bots that go underneath something, you can grab a pallet and take it away. We can use this AMR system, this shelf-level AMR system, to come in and manage which pallets are available at a robotic cell at any point in time. So that's it. Like in this image, I have a robotic cell that has 7 put 2 positions on it. That's a pretty big cell. But I can swap out those pallets such that I can effectively service 10 or 40 or 100, depending on the rate that I need to achieve for that robot cell. So you can multiply the number of sortways that are available to be serviced by a single cell by having an efficient system to manage what is in those put positions. And in this case, and we've done this with pallet conveyor in the previous example, or pallet crane and ASRS. And in this case, we're approaching it with another robotic solution. So robotic AMRs. Pretty clever, pretty low infrastructure cost, and probably a pretty excellent solution to explore if you have a high pallet count and kind of that middling throughput count. And similar to the pallet conveyor discussion, because I already have a pallet being taken away from the system on a piece of technology, I could probably go ahead and tie that technology to some ancillary process. You can run an AMR into a strapper or wrapper pretty easily. And that's kind of a great additional benefit of a solution like this. Now let's talk about something that's a little bit more exotic. So this is a rendering of something called a gantry. So this gantry is this big long rails, let's say in the X axis, and it has these big gantries that ride across in the Y axis. And inside of that gantry, there's a little robotic head. So and that'll move in the Z axis. So each of these blue units can travel the length of this system and access any of these pallets. And in this way, they can cover hundreds of pallets per robot. So the buffer in this case is just internal to the robot cell. So whereas a 6-axis robotic arm that accesses 6 or 8 pallets is on the larger end of a system like that, here it's completely reasonable to assume that these robots could access 450 pallets at a time. And there's several ways to set these up, and no two are the like. But you could have these systems, as in this image, serviced by pallet conveyor. So, pallet conveyor brings pallets in and it builds onto the pallet conveyor and takes the full completed pallets out of the system. That's definitely an option. You could also have a system like this that's serviced by the AMRs that we showed in the previous example. So an AMR will drive in and set the pallet in somewhere in this service grid. And then the gantry heads will go ahead and pick off of that or build to one of those positions. And then the AMRs will be triggered that, hey, take this load away. So we'll go take it away and put a new one in that place. So definitely a lot of options on how these work. Here's another example. We have a field where it expressly shows the AMRs servicing that gantry field. And you can have a single head or single gantry bot riding on those rails. You can have multiple heads, although past 2 does get pretty wild. So typically the most you see is 2 in a single system. And the field can be expanded or contracted based on the number of sort ways that you need inside that field. So I think in this example, we have something like 50 to cover 40 destinations. So it's kind of some overkill. But the last example was, I think, 450-ish kind of target locations in that field. So pretty powerful stuff. And similar to the other robotic systems, you can do single case, which is what we showed in the last images, or you can do rows of cases, or you can do layers of cases, provided you feed and present those totes or cases in the appropriate manner. The more things you pick up at a time, the faster your totes per hour will be, just like the other robotic solutions. So that does present an excellent option for these type of systems. Now, you'll often see a system like this used in a layer pick environment, just because it's a fairly high capital kind of entry cost, and you want to make sure you get lots and lots of rate out of it all the time. And so they're very often in layer pick operations, but not exclusively. And then there's kind of one other technology, and this is a much more traditional, I guess is the best way to say it, technology. This is a unit load former, that's what I call it, but it's more of a mechatronic way to build pallets. So in this case, you'll have totes or cases or something come in, and they'll be arranged through some kind of mechanical processes of conveyor and alignment, and maybe you have a case flipper that comes and pushes the case into a certain orientation, and they'll kind of build each layer on a planting, to just use a word there. So on a surface, and that surface will then be retracted in some way and allow that layer to be set on top of a pallet or the previous layer that was built. So here you build a layer on the surface, and then you set it on the pallet, and you build the next layer, and you set that on the pallet, and you build the next layer, and you set that on the pallet. These have the same kind of cool ability to connect to ancillary systems that all of the pallet conveyor-based systems and AMR systems have. So you can run this right into a wrapper. Some of these systems can even wrap while they're building the pallet. Super easy to integrate into stuff, and you can build tote or pallet destackers into them so they can automatically put the next pallet in there. The one note is that you do need to be pretty locked down on how you sequence to these systems. Oftentimes you'll see them used in production facilities where they're building the same SKU and the same layer pattern again and again and again. And they're pretty excellent for that. It doesn't mean you can't use them for other things, but you do need to kind of pay attention to your data and ensure that you're going to have the right mix for this type of machine. Okay, so let's talk about some weird behaviors we see. So I'm going to use some costs. These are not validated numbers. These are just some inputs to the model to kind of give us some tangible takeaways to think about and to talk about. So what's some things that, as we put this together, we sort of realized that we needed to kind of share a little bit more is when you change the characteristics of the system. So when you get different design requirements for a system, the technology you end up selecting is not going to be the same. So in this case, we have on the left side, a system that runs at 4,000 totes per hour, but only needs to service 2 destinations. And what we see is that we probably tend towards the simpler 1-to-1 or 2-to-1 style robotic systems. I don't need a lot of destinations, and so it doesn't make sense for me to have these big systems where I can serve lots and lots of destinations. I just don't need them. I do need a lot of robotic capacity. So in this case, I'm going to buy the number of robots based on the number of totes per hour that I need to achieve. On the far right side, what we see is a lot of destinations. So 100 destinations that we're going to build, 100 target pallets we want to build to at a time, but only 1,000 totes per hour. So here we're not going to go as fast. And this is a quarter of the speed of the first example, but it's, 50 times more locations. There's a lot of locations. And in these examples, systems that service lots and lots of destinations tend to shine. So gantries, in this case, like specifically the layer gantry and the row gantry, they look excellent because I'm going to be able to hit all those destinations very easily, right? And I don't have to make that machine that doesn't move super fast, right? I don't need all that extra rate. I do need the destinations. And in the middle here, we have this 2,000 totes per hour and 40 destinations we want to target. So it's kind of an in-between case, if you will. And what you see is the things that start making the most sense are these medium complexity robotic cells. So 4 and 6 cells, and we're going to sort to them. We'll do a little bit of work there. But they start to make the most sense. So depending on your design requirements, depending on the characteristics of the final operation that you want to have, the technology selection is going to be different. And this is definitely something that, we as integrators, try to take as much time as we can to understand everything about your operation and then really dial that in. One note is we have this mismatch count here. And this is kind of a little metric I made up, a bit of a rule of thumb, if you will. And what I do is I compare how many robots I would need for these systems to service the throughput, and then how many robots I would need to get the right number of pallets to destinations, right, to target destinations, and see what the mismatch is. So in this case, with the 2 destinations, there's a very small mismatch between those 2 numbers. I only need 2 destinations, right? But I need a lot of robots to hit rate. So I'm only like 3 apart in absolute terms in these 2. But here and here, right, I need 100 destinations, but each robot only does 1 pallet. Well, I'm 98 off because I need to buy 100 robots to hit 100 destinations in this case. But I only probably need 2 robots to accommodate the throughput that's required, this 1,000 TPH. So I'm 98 apart. I have a mismatch of 98 robots between capacity, the throughput capacity, and target destinations. And this mismatch, if you kind of think about it that way, will tend to predict what type of solution is going to be the best. Whatever has the least mismatch is going to end up yielding the lowest capital for that scenario. Oftentimes, it's not 100% true all the time, and there's definitely a lot that this model doesn't take into account. But it's definitely kind of some food for thought here. It minimizes you overbuying, and that overbuying problem, it leads to increased capital in many circumstances. Now, if we do the same kind of analysis, but we kind of dial things in a little bit more and we auto change out pallets, then what happens is that this behavior changes pretty significantly. So let's say I'm using an AMR-based solution to automatically swap out pallets from cells. Well, what happens is I end up making every robot cell similar to a gantry that can service as many destinations as it needs to service, right? It's not universally true, but it starts to look like these 1-to-1 or 1-to-2 robot cells can service 40 destinations or 2 destinations. So what happens is when I auto change out pallets, I end up correcting for most of these mismatch issues. And then I can use, a more complicated exchanging system, but it's much simpler and much less expensive robotic system to achieve that rate. So now I'm getting the right amount of robots for the rate, and I'm solving for the destination count with my exchanging systems and or my buffering and sequencing systems, if those are of sufficient size and scale. And here's a kind of a scenario to really try to hammer the point home. But we have this 2040 scenario in both cases. On the left side, this is the traditional, pallets have to be swapped out the hard way. And the gantry system looks pretty great in a layer regime, if I can achieve layers. But alternatively, like in normal, operation with singles or rows, the 1-to-6 robot looks pretty good. And you'll see robotic cells like this out in the wild just because of this behavior. But if I auto exchange, then suddenly what looks great in a lot of cases is these simple, really fast robotic palletizing cells. Now you'll notice that as the number of destinations increases for robotic cell, so too do we believe that the rate of the throughput would decline. And that's sort of what we model in here. That's kind of a note. And that's why this sort of happens. One big note, and kind of getting close to the end here, so thanks for sticking with me. We want to, when we're designing these systems, we want to look at your design requirements. And so that means we ask the data what the right targets are for us to design this. As we discussed earlier in the presentation, depending on your goals, how much throughput do you want? How many destinations do you want? How much weight does everything weigh? Like, these impact the technology selection. It's not just different like positioning. We might select completely different technologies depending on different design requirements. And there's, this is evidenced by the amount of equipment and different arrangements that are available in the market today. But let's focus in on one case here. So 2,000 totes an hour, 40 destinations. If I did it with a simple kind of pallet building robot cells and then some inbound buffering, the simplest type of inbound buffering, then I'd want probably 3 robots, and I'd want a buffering loop here that would sequence into these robotic cells to be pretty robust in terms of its ability to store things. So I'd probably need to store like 920 totes or something in this kind of arrangement. So that's not impossible, but it is a bit of a lengthy conveyor. It's not really shown here. And I'm going to be running these 3 robots pretty hard. So if I actually go in here and exchange a pallet, it is going to potentially cause me some heartache. So I can accommodate for that pallet change out by making these double pallet cells, which probably don't lose any rate, or I can just add a couple of robots and make my whole system more robust anyway. So a couple pieces to think about there. If I were to solve this 2,000 an hour and 40 totes with a kind of a medium complexity robotic cell, these 6-to-1s, for example, it might look something like this. This sorter is really just saying, hey, this tote goes to cell 1, this tote goes to cell 5, this tote goes to cell 6. That's really all it's doing. And it holds some additional inventory for when these guys are doing changeovers. But that's about it. But you're going to have a safety fence. It's going to be a pretty big system. You have to have so many robots, and each robot cell has so many pallet positions. They begin to become pretty large systems with a lot of capital and a lot of footprint. And then if we look at this kind of gantry option, so streaming all of your totes to a large multiple robot or multiple pallet system, so like a gantry, this in certain circumstances is pretty great. Now I will say that in the 40 destination and 2,000 an hour range, what tends to happen, or what we've seen here, is that I can service all the destinations in one field. That's fine, but I'd probably need, in order to make the rate work for these systems, I'd need to have 2 of these gantry heads, and they would have to work at a layer level in order to have the right amount of throughput. So this is going to imply that I have enough buffering feeding these things to hold all of the totes that I would need to make, to provide single layers to the gantries at a time. I'd probably have to have something like 200 totes in waiting, so that I can build up enough to make a layer to give the gantries pure layers. Now, I will say that when this is full, the AMR is going to take it away, and so it's also very highly automated. This is minimal interaction, but definitely an interesting solution. The lower the throughput, the more attractive these get. And here's an option with the AMR swapping of the kind of normal robotic cells. So totes are going to flow in based on the general destination. So I show 7 pallets per cell, but you can probably have totes flow in pretty regularly for 12 or 15, destinations, and just let the robot manage the pallet positions itself. So we'd have software that would coordinate all of this stuff, or orchestrate it, if you will. What we often see as well is that pallets are kind of normally distributed. So you'll have some fast destinations and some slow destinations. And it's probably the case that the fast destinations would always be present at the robot cells, and the slower destinations would be the ones you swap out. Maybe that tote sits in the line for a little bit longer while the robot brings over a slow destination and swaps out an old slow destination. So that would be kind of what that arrangement would look and feel like. And here, there's minimal downtime because we're interacting with all this pallet exchange in a robotic fashion. So there'd be minimal downtime. There'd be minimal buffering and sequencing on the in-feed. And you'd be able to automatically connect it to downstream automation. So pretty excellent outcome, really. Thanks for learning about pallet building arrangements with me today. I know this is kind of an interesting topic, and some parts of it could be complex. Sometimes we go through it pretty fast, kind kind of the nature of the beast. If you want to learn more about it, check out Hy-Tek Intralogistics. We'll probably have some links to our website and some additional content wherever you found this video.